It is part 2 of section 2.1, properties of matrix multiplication. In the first part, we studied matrix addition, subtraction, scalar multiplication, and matrix multiplication. Here, we'll begin with this example, matrix multiplication, and we'll consider some other properties of matrix multiplication. Okay, compute A, B if A, B are given in this way. Now A, B, then from here, okay, matrix multiplication is here now row, column, dot product, and we collect those dot products. And first row, once we are choosing first row, then first column, then dot product will be, okay, 2 times 4 and plus 3 times 1. That's the first entry. And the first row, the second column, that is now 2 times 3 and plus 3 times minus 2 plus 3 times minus 2. That's a second entry. And now third column, then 2 times 6 and plus 3 times 3. Right? Okay. Now for the second row of AB, we start with now second row, okay, that one, and first column. So 2, 1, that is a 2, 1 position, and 4, okay, 1 times 4, and plus minus 5 times 1, right? Okay. Now for that one, second row, second column, and 1 times 3 plus minus 5 times here minus 2. And the final entry is second row, third column, 1 times 6 plus minus 5, okay, minus 5, okay, times here 3. Okay, so you can simplify. There's a plus 3, 11, and 6 minus 6, which is 0, and there's 21, and 4 minus 5 is minus 1, 3 plus 10 is 13, and 6 minus 15 is minus 9. Okay, that's the final answer. Okay, find all columns of B if A and AB are given in this way. Okay, here we write down here A, 1, 2, minus 1 and 3, and B must be found here. We'll find this B, and then AB is now 8 and 7, 7 minus 2. Right? Okay, for that one, okay, here the result has 2 columns, so that we have to have 2 columns. Right? And then now here the A has 2 columns, so the number of row must be 2, so that we have to fill out here this, that, and that. So here B must be a 2 by 2 matrix, so that this multiplication can be defined along with these 2 rows, because it has 2 columns, so they're the same. And now here right side, the result has 2 columns, which means that here we have to have here 2 columns in B, right? Okay. So here now this first column will be product of this matrix and first column, right? So that eventually, if we say that is now X and that is Y column, then eventually we have to solve AX equal the first column 8 and 7, then we can find X. By solving this problem, we can find the first column of B, and the matrix times this second column made this second column, so that here A, Y equal here, 7 minus 2. We have to solve these two problems to find X and Y, and we can finish the computation. Okay, how we can find them? By using augmented matrix. So here, for this one, here the augmented matrix is 1, 2, minus 1 and 3, and 8 and 7. Right? Then from here, by adding, here 1, 2, 8 is changed into 0. Addition is 5. Addition is 15. So that is 1 and 3. Divided by 5, it can be 1 and this is 3. And twice subtraction will make here, and 1, 0, 2, 0, 1, 3. So that's the answer. So here, first column of B must be this one, 2 and 3. Now, how about second column? The exactly same way we can find Y. And A is, again here, 1, 2, minus 1 and 3. And right side is 7 and minus 2. Okay. Now, from this one, by adding, here 1, 2, 7 is 0 and 5 and 5. Divided by 5, it will become here 1 and 1. Now, we can reach it here by twice subtraction is now 1, 0 and 5 and 0, 1, 1. So Y must be this one, which is the second column of B. Right? So we found the first column, second column of B, and we finished computation. Of course, you can do this one simultaneously. Now, rather than separate here the columns from AB, you may put the whole together, so that here we start with in this way. Okay, that is this is A, and 1, 2, minus 1 and 3, and we try to add two columns simultaneously, so the 8 and 7 and 7 minus 2, and then we apply elementary row operations. Okay, so the 1, 2, 8, 7, and addition makes 0, addition makes 5. Here that one, addition makes 15, addition makes 5. You can see here now the pattern. Okay, 8 and 15 is this one. You can see that. And then 7 and 5 is this one, right? And divided by 5, we reach at, and 3 and 1, which is this one and that one. And after eliminating this term, we can reach at, and this portion becomes 2, 3, and 5, 1, right? You can do it simultaneously. Okay. Find the first column of B if A and AB are given in this range. So here, okay, A, let's write down some detail, minus 2 and 3, 3, 3, 5 and minus 3. And then here, along with this matrix, and B, okay, and then we'll have here AB minus 11, 9, and 23. And then here another column. Now, we want to find the first column of B. So this column, okay. So that is, if we say this is X, then matrix times this first column will make this first column. So we have to solve the problem, and here for now AX equal the AB, and here now first column, right? Then if we can find X, then that's it. Now it has two columns, which means that B has two columns. And again, here, now A has two columns, so that the number of row must be 2. Right? So that we have basically here something like that. 2 by 2 matrix. Right? So we have to find this first column, 2 entries. Now, exactly the same way you can find it, along with the augmented matrix. So let's start with this matrix A, minus 2, 3, 3, 3, 5, minus 3. And then right side must be minus 11, 9, and 23. Right? Okay. From this one, now we need to make this position 1, and in order to do that, you can scale that one, but it's not integer. So once you are using your hand computation, you have to do something else anyway. Okay, let's add them over there. And the second way it's added then is 1 and 6, and here there's minus 2, right? And then this is now here 339. Okay, you can also divide by that one. There's 113. Okay, that is basically same as here 113. By subtracting this row, it'll be 0 and minus 5, and then that is 5. Okay, now, and 5 times subtraction, or 5 times subtraction from that one will be fine. Then that will be 0. 5 times subtraction will make that one minus 8. And here 15 and subtracted, so that will be 8. Divided by minus 5, divided by minus 8. This one will be 1 and minus 1, 1 and minus 1. So let's write down the result here. 1, 6, minus 2. 0, 1, minus 1, 0, 0, 0. Right? Okay. Now we have to reach at the reduced ratio form. 6 times subtraction. Then 1, 0. 6 times subtraction means 6 is added, so it is 4. And here 0, 1, minus 1, 0, 0, 0. Now this the answer is this column. It has 2 components, so that is the solution, right? 4 and minus 1 is the first column of B. Okay. Okay, here commutativity. Suppose both AB and BA are defined, then in general AB and BA are not the same. For example, here A and B are defined in this way, 2 by 2 matrices. Then if you try to get AB, then this one BA, then you have that, so they are not the same. For cancellation here, if you have AB equal AC, then here in general you cannot cancel A, so that here if you cancel, then you can get B equals C, but it's not necessarily true. For example, if you choose trivially A is 0, then no matter what B and C are, it doesn't matter. AB will be 0, AC will be 0, so they are the same, but B and C are not the same. Here, but sometimes it is true. That is related with non-zero determinant. We learn this concept, and also very soon we learn invertibility. And once A is invertible, it means it has inverse. Then we can multiply A inverse both sides, so that this part will disappear, so we can get B is the same as C. Except that, yeah, it's not necessarily true. Okay. Power of a metric. If A is an m by m metric, a square metric, and if k is a positive integer, then a to the k denotes the product of k copies of A. So k times multiplication is written in this way, a to the k. Once k is 0, then we consider a to the 0 as the identity metric. Okay, and this is a convention. Like for real numbers, a to the some number scalar from earlier in elementary school or high school, you learned that a to the power 0 is 1, right? You learned that one. The same way, now for metric domain, a to the 0 is identity. The metric A and power 0 is identity. Okay, you may consider this one as a definition. Okay. Okay, here we have a transpose of a metric given on m by n metric. The transpose of A is, now we use the notation A super T, and whose columns are formed from the corresponding roots of A. That means that here, if A is denoted by an Aij, then here A transpose is here Aj. So column will become row, and row become column. Okay, if A is given in this way, in this example, and A transpose will become in this way, the first row will become first column, 1 minus 4, 8 and, okay, 8 and 1. Now, second row will become second column, 0, 2, minus 1, and 3. And third row will become the third column, and 0, 0, 0, 5. And you may think here, first row changed into first column, but you're thinking in the other way. First column becomes first row, second column becomes the second row, and so on. Either way, you can consider the transpose. Okay, here in the theorem, we summarize the properties of transpose. A is written in this way, Aij, then A transpose is Aj. Row and column are changed. Once you make a transpose and one more time transpose, then the result will go back to the original one. And for summation transpose, then there is a sum of transpose of each one. And for scalar multiple, you can multiply all outside of transpose or first multiplication and then transpose. Either way, you can do it. Now, you have to be careful for this one. AB transpose. That must be same as B transpose, A transpose. You have to change the order here. For the examples, the 30 examples, you can check this one quite clearly. So I will not prove that. However, you have to be careful when you are trying to transpose the matrix multiple. Here you have to change the order. If we apply this property recursively for the multiple of 3 matrices, then here you have to get this one. ABC transpose. So must be now transpose of here C, transpose of B, transpose of A. Exactly opposite order. So you have to use in this way. Okay. Okay. Now here we have a true or false problem. Okay. Each column of AB is a linear combination of the columns of B using weights from the corresponding column of A. Is it true? That is false. Okay. In fact, if you change here A and B, exchange, then it'll be true. Each column of AB, and after product, the column is a linear combination of the column of A using weight from the corresponding column of B. Then it is a correct statement. The given one is false. The second row of AB is the second row of A multiplied on the right by B. Is it correct? Yeah, it is true. And here, second row in AB multiplication is A and that is B. Then it will make AB the result, so that the second row, that one, is made in this way, and from the second row of A, and we try to make the dot product of the columns from B, and each one will make an entry here. So that is exactly explaining that. Second row of AB is the second row of A multiplied on the right by B, right? Okay, so that is true. The transpose of a sum of matrices equals the sum of their transposes. Is it true? Yeah, that is true. In fact, that is exactly this one, the C here. Okay. Now we have some challenging problems. Show that if the columns of B are linearly dependent, then so are the columns of AB. Okay. Here, linearly dependent means that, the columns of B are linearly dependent. That's the same as here, if you have, not A. And if we have a linear system, for example, B of x equal 0, then linearly dependent, then it has non-trivial solution. If the columns of B are linearly independent, then there is no non-trivial solution. It is only trivial solution. But once it is they are linearly dependent, then it is a non-trivial solution. So Bx equals 0 with a non-zero vector. And here again, if you multiply from this equation, then ABX must be again 0 because it's 0, so that it must be 0. That means that AB has non-trivial solution. Same x is the solution, so that AB x equals 0. So we can consider now this one is a metric. This metric, the homogeneous problem has here now non-trivial solution, so that here AB itself, the columns of AB must be linearly dependent, right? Suppose CA is identity for some matrix C, show that the equation AX equals 0 has only the trivial solution. Okay, for that one, now, okay, it's quite simple. Already, this one is given, so that for that one, here, if we want to find the solution, and anyway, we have to solve this algebraic system, but CA is given to be identity, so we multiply C both sides, then C A of x equals C times 0, which is 0. But CA is identity, which means that x, left-hand side of the x, and equals 0. The solution of this equation, this system, is just the trivial solution. So we prove that, right? Okay, this is end of the section. Thank you.